How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our business today is the classic adventure of Archimedes, about the 3rd century B.C., with some wondrous things to report. First, consider a body, a lead weight, which I hang on a spring scale, and the scale reads so much. I am not interested in what it reads, but it reads the weight of the body. Now let me submerge this body in a vessel of water, and we see a remarkable thing, a very remarkable thing. As I submerge it, the scale reads less and less and less, and I urge you to see that the weight is not resting on the bottom of the vessel of water. Accordingly, when I submerged the body, the water pushed up on it, provided a buoyant force, as we say, which Archimedes discovered in his classical bathtub experiment. Eureka, eureka, I have found it. Now, how much is the push up of the water on a body submerged? Archimedes said it this way. When a body is submerged in a fluid, that's either a gas or a liquid, we're talking liquids here. When a body is submerged in a liquid, it is buoyed up by a force equal to the weight of the liquid displaced. Now, I can prove that. Here I have a vessel which has an overflow spout, and I'm going to put a little water in it to be sure the water is up to the level of the spout. There it is. It's coming out there somewhat. And now I'll wait until it stops. The water is up to the level of the spout in this chamber. Now, I'm going to get rid of that water. Now, what am I going to do? I'm going to submerge this body in that chamber of water, and as anyone in his right mind would recognize and attest, will not some water be pushed out? Indeed, and I'm going to push some water out and catch it in that little bucket. Watch it now. And, of course, again, the scale will read less, but I'm not interested in that this time. I'm interested in the water that gets pushed out. Watch it now. And I'll wait till all that's going to be pushed out is pushed out. That's good enough. Now, what would I do with these adventures? Well, first I would have noticed how much less the scale read when the body was submerged in the liquid. Suppose it read less by 10 grams. Then I weigh this water in this bucket. And what would the water in this bucket weigh? 10 grams, meaning that the body was buoyed up by a force equal to the weight of the water this body displaced. Archimedes' principle. Fantastic. Now, I said that the water pushes up. I'm going to prove that. Indeed, you should recognize it already from your adventures by the sea. When you walk into the ocean, do you not discover that the deeper you go, the less push your feet have on the earth below? Because the water is buoying you up more and more, the deeper submerged your body becomes. Here I have a glass and a hole in the very bottom, and I'm going to push the glass down. The evidence that the water pushes up will be witnessed by the water coming up into that hole. Watch it. There it is. There it is. And I say the water pushes up. I'm going to prove that in another way. Here is a glass tube and a plate on a string. And I'm going to put the string through this glass tube. And now I'm holding the string in hand. And obviously, since the plate has weight, if I let go of the string, the plate will fall down. Watch it. Well, of course, there's anyone who's watching. Doesn't that professor know that if you let go of the plate, it'll fall down? Of course it'll fall down. Now I'm going to prove again that the water pushes up. Well, how? I'm going to put this into the water, and instantly I make connection with the water. I'm going to let go of the string. When I let go of the string out here, the plate fell off. The plate will not fall off in there. Watch it. There it is. And you see water rushing into the inner cylinder, climbing higher and higher, and everybody says, well, when it gets the same height inside the vessel as outside the vessel, then the plate will fall off, and I'm going to leave that for you to think about. But now, my new adventure, Archimedes' bucket and cylinder. I have here a little bucket, very nicely formed, and a solid cylinder which fits it exactly, And here's what I'm going to do. I'm going to balance this bucket. I'm going to balance that bucket with the cylinder below. Let me see if I can represent that. Here is the cylinder below. And remember, that solid cylinder fits that bucket exactly. And I'm going to balance this with some weights over here. Put the beam balance in equilibrium. Then what am I going to do? I'm going to come up underneath with a vessel of water in this fashion. Vessel of water, so that I submerge the solid cylinder. The equilibrium in the balance will be destroyed, as we might say, because why? The water here is pushing the cylinder up. How much is it pushing the cylinder up? It is pushing the cylinder up with a force equal to the weight of that water displaced. And how much water is displaced? The volume of the cylinder. And how much is the volume of the cylinder? The volume of the cup. Accordingly, with the equilibrium destroyed because there is a lift, a buoyant force here, I am now going to pour some water into this little bucket. Water, 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 water. Oh! When this bucket gets full, what will we see? An absolutely enchanting thing. We will see the equilibrium restored. Now I have such a bucket and cylinder. There's the cylinder, there's the bucket, and I have put it in equilibrium on the scale. Now I'm going to bring up this water and submerge the lower solid cylinder. I hope you see that the equilibrium has been destroyed. The balance is no longer in balance. Oh, I came up too high. Now I am going to fill the little bucket. I'm having a little trouble here being steady. I'm going to fill the little bucket, and the equilibrium, which does not now exist in the scale reading, will be restored. Watch me now. Oh, I filled it over much, and there's a very high meniscus. So, Archimedes' bucket and cylinder. The proof is very beautiful. A body is buoyed up by a force equal to the weight of the water displaced.